On October 13, 2025, SpaceX's Starship did something the world had never witnessed. A successful in-space engine restart, the deliberate removal of heat shield tiles mid-mission, and the flawless deployment of 8 Starlink simulators. This marks the first time Starship proved every critical step toward deep space travel in one flight. But how did they pull off what everyone said was years away? T-0. Starship's engines ignite in a blaze of methane and oxygen, and the world's tallest rocket thunders off its launch mount at exactly 23:23 and 36 UTC. 33 Raptors roar in perfect unison, pushing the full stack through the dense Texas air. Just over a minute later, the vehicle surges through max Q, the point of greatest aerodynamic pressure, every sensor and camera glued to the data. By 3 minutes and 16 seconds, the Super Heavy booster's main engines shut down, and almost instantly, the stage separation sequence triggers. A sharp cutoff in the exhaust plume signals the split. The booster begins its flip for splashdown, while Starship's upper stage continues its climb. Mission Control confirms separation at T plus 3 minutes and 19 seconds. In those first few minutes, every system is tested, every objective checked. The timeline is relentless, the margin for error razor thin. Each checkpoint flashes by: liftoff, max Q, MECO, separation, paving the way for what comes next. The moment Starship must prove its mettle in space. Minutes after separation, Starship glides through the silence of space. The coast phase begins. No engines, just momentum and anticipation. At the 11-minute mark, controllers send the command. Deep in the vacuum, a single Raptor ignites, its exhaust blooming into a pale blue fan against the darkness. This is the first time a Raptor engine has restarted in space on Starship, a feat essential for future missions to the Moon and Mars. Sensors confirm stable combustion, chamber pressure steady, all systems green. The engineering team, scattered across consoles in Hawthorne and Boca Chica, watch the data stream in. Moments later, the payload bay opens. 8 Starlink simulators release, drifting free in a carefully timed sequence. Each one stands in for a future satellite, proving that Starship can deploy or go in orbit. As the bay closes, Starship rolls, orienting for its fiery return. The next challenge waits on the edge of Earth's atmosphere. Reliability in spaceflight comes down to what happens deep inside the rocket, where metal, fuel, and fire meet. Starship's Raptor engines rely on a full-flow staged combustion cycle, a design that feeds both methane and oxygen through separate preburners before combining them in the main chamber. This approach squeezes out every bit of efficiency, but it also demands flawless timing, especially when an engine must restart in the vacuum of space. To make that possible, Starship carries specialized header tanks, smaller reservoirs nested inside the main tanks. These keep a reserve of super-cold methane and oxygen, ensuring that even after a long coast, the propellants are ready and settled for ignition. Instead of using heavy pressurization systems, SpaceX engineers turned to autogenous pressurization, heating a portion of the propellants to gas and feeding it back into the tanks to maintain pressure. This method reduces complexity and risk, allowing precise control over tank conditions. When the command comes, a tightly choreographed sequence begins. Valves open, turbopumps spin up, and torch igniters fire at just the right instant. The result is a controlled burst of combustion, even in microgravity, where nothing wants to stay in place. Every restart is proof of the system's logic. Hardware, software, and physics working together, all designed by engineers who know that in space, there are no second chances. Engineers at SpaceX decided to push Starship's limits by removing clusters of ceramic heat shield tiles from critical areas, along the belly, around flap hinges, and near the tank domes. The plan was simple, but bold. Expose bare stainless steel to the full fury of re-entry, then watch what happens. As Starship plunged back through the atmosphere, infrared cameras captured streaks of orange and violet plasma racing across the hull. Hotspots flared where the tiles were missing, revealing just how much heat the underlying structure could take. On the aft flaps, the most extreme temperatures left visible scars, charring, streaked insulation, and signs of metal oxidation. But the structure held. The two-layer protection system, a primary shell of ceramic tiles, backed by flexible ablative fillers and a mat of silica fiber, absorbed and redirected the worst of the plasma. Post-flight images showed localized damage and microcracks, but no catastrophic burn-through. The experiment didn't just prove resilience, it gave engineers real evidence that Starship can survive even when things go wrong. Every Starship flight, especially the ones that ended in fireballs, became a lesson. When SN8 tumbled out of the sky and SN11 vanished in a shroud of fog, engineers didn't flinch. They circled the problems. Each crash sent teams back to the drawing board, tracing the cause to everything from propellant plumbing to software timing, and even the bolts holding flaps in place. Plumbing was rerouted, software rewired, structures reinforced. Overnight, hardware would change, and by morning, a new version stood on the pad. This relentless cycle, test, fail, fix, repeat, became the backbone of progress. Every scar on the landing zone pointed to a breakthrough waiting just ahead. Silence swept through the control room as the final data streamed in. Eyes locked on screens, hands hovered over consoles. Then, a single confirmation. Engine shutdown. Splashdown. Successful. The tension broke in a heartbeat. Cheers irrediton. Some engineers pounding the desk, others just grinning in disbelief. Out at Starbase, the crowd's roar echoed across the flats, car horns blaring, strangers hugging. For a moment, every setback and sleepless night vanished into pure celebration. The impossible, at least for tonight, was real. On October 13th, 2025, SpaceX's Starship Flight 11 became the first mission to achieve 3 consecutive in-space engine restarts and a deliberate heat shield tile removal test, all verified by real-time telemetry and public webcast footage. These feats mark a turning point after 5 earlier failures and years of engineering iteration. The evidence, visible engine relights, successful payload deployment, and booster recovery, confirms major progress toward fully reusable, high-cadence spaceflight. Yet some details remain classified. Full post-flight TPS erosion data and specific redesign schematics have not been released. What is certain is that each test, success or failure, directly shapes the next flight. Today's breakthroughs are the result of persistent problem-solving, as shown in mission logs and engineering reports. As of this flight, Starship stands as the only operational vehicle to validate these maneuvers in a single mission. The path ahead is defined by evidence. Every launch, every lesson, and every documented result brings humanity closer to routine, ambitious journeys beyond Earth.